Okay, so we will continue with the course material on fins. We have already studied together how a fin can enhance the performance, cooling, or heating of a certain surface. Okay, and we have derived together the differential equation of variation of temperature with position. And this differential equation is really based on a simple energy balance for a small element. So if I take, for example, this element, I have that heat is conducted through the fin. Just 1 second. So heat is conducted through the fin. I have Qx here and Q at x plus dx. And at the same time, I have heat that is lost by convection to the outer environment. So if I write the energy balance for this small element, I get the following equation, and we did it together. Okay. Now, if you remember, we said this differential equation has a certain solution, and I will always give you the form of the solution. You don't have to memorize it. So this is the form of the solution for such equation, and we did a change of variable. We considered theta to be t minus t infinity, and we considered that hp over ka is a constant that we name m squared. Okay, and the value of m will be used in the solution because the solution of this equation is theta, which is t minus t infinity. T, if you want, is the temperature, which is varying in x. So at any location x, I can solve for the temperature. And T infinity is the surrounding temperature here. So theta is equal to C1e minus mx plus C2e mx, exponential. Now, depending on the boundary conditions, we solve for C1 and C2. Let us take a very simple case first. If I take case 1, if I consider that the fin is very long, whenever they tell you the fin is very long, then we can consider that at the end of the fin, okay, the heat flux is equal to 0. So Q second at L is equal to 0. This is what we mean by the fin is very long. Okay, so how we can write this as an equation? The fin is very long means that at x equal infinity, okay, since no heat flux at the end, this means that the temperature at the end of the fin should be equal to T infinity because no heat transfer is taking place. So that's why we can say that this sentence means the following condition, that theta, which is T minus T infinity, is equal to 0 at x equal to infinity. Now, if we apply this condition here, so we put 0 equal to, you know, if I consider, when I consider x tends to infinity, then this term will drop. Okay, so this is 0 plus C2 times exponential of infinity. You know that exponential of infinity is infinity, but how it's possible to get infinity times a constant equal to 0? The constant should be 0. So we deduce from this condition that C2 is equal to 0. Okay, and we just have for this condition, when the fin is very long, theta can be just written as C1 times exponential minus mx. Okay, now we still have to solve for the other constant C1, so we need another boundary condition. In general, they gave us, they can give us at the base. So at whenever we say the base, it's here. So at the base level means x equals 0. They can give us the temperature of the base. So if I call this TB, okay, or T0, then if I give you T0, you can say at x equals 0, I know what is theta. Theta is equal to T0 minus T infinity. And now I replace in my equation. So I can say that I replace theta 0 by, so theta 0 equals to T0 minus T infinity equals to, you know, if I replace x by 0, I get my constants here. If you put x equals 0, this is 1. Okay, so I just get C1. So my constant C1 is simply equal to theta 0. And then I can say that my equation is of the following form. So theta is equal to theta 0 times exponential minus mx. This is the solution for this particular case, okay? And if you take theta 0 to the other side, you get theta over theta 0, which is t minus t infinity over t0 minus t infinity equals to exponential minus mx. So this is the solution for our first case, okay? Any question on this?
No.
No, Doctor.
All is clear, Doctor.
Okay. Now we can change boundary conditions, as you know. Okay. For example, let's say instead of telling us that it's an infinite long fin, we can impose a adiabatic condition at the end of the fin. Okay. So in this case, we say that at x equal L, adiabatic condition means heat flux 0. So dt by dx equal to 0. Okay, but the only difference now is the following. Instead of saying at x equal infinity, we have that theta equal d theta by dx equal 0, it's at x equal L. And because of this, the form of the equation of the boundary will change. But the concept is the same. Okay, so if I consider first that I know at x equals 0 what is the temperature at the base, I replace here x by 0, so this will give me 1, and this is 1. So theta 0 equal to C1 plus C2. This is my first equation, which is similar to the one we did before. But what is different now is that instead of saying at x equal infinity, okay, I have a flux of 0. In this case, I have at x equal L, d theta by dx is equal to 0. And you know, this is theta. So what is d theta by dx? I just have to derive. So d theta by dx equals to, I derive, so the derivative here is minus mc1 minus m times c1 e minus mx okay, and plus mc2 emx. Okay, and now if I replace at x equal L, so I just have to put here L and L. Okay, this should be equal to 0. So I get the following condition. Okay, I get the following condition, and now I have two equations with two unknowns. I can solve for the values of C1 and C2. Okay. Don't worry about these function forms. Okay, I will give them to you. I just want you to know how to apply boundary conditions and how to get your C1 and C2. Okay. Now,
Doctor,
yes.
concerning these conditions, we can easily identify them from the given,
Yes, of
know
course.
which one to use.
Yes. يعني if they tell you, if they give you a certain length of the fin, not infinite, okay? If they don't tell you the fin is very long, if they tell you, for example, the length of the fin is 100 millimeter, you cannot consider that it's an infinitely long fin, okay? But they should tell you, for example, the end of the fin is insulated or is adiabatic. Or another possibility, let's say they can tell you we impose a convection, we have a convection with the end of the fin, and they give you the convective coefficient, and you work as we did usually. If they tell you you have convection at the end of the fin, what do? You say at end of the fin, Q second, okay, that will exit. So Q second at L, okay, is equal to, if it's evacuating here, let's say by convection, so is equal to is a convective coefficient H that will be provided times T at L minus T infinity. And it's like the conditions we are used to do before. Okay?
Okay, thank you.
Welcome. Okay. Now, another case is that this is what we were talking about now. If you have the fin is of finite length and losses, we have loss of heat by convection from its end. Okay, you are not responsible, as I told you, of getting the form of the equation. It's really complex and it's a mathematical solution. I just want you to know how to write the conditions. And if I want you to find temperature profile, I will give you the formula. I will give you, I will show you a table. I will show you a table where they put for you, depending on the case, what is the temperature variation function of x. But just you are responsible to know how to find C1 and C2 by applying the appropriate boundary conditions. Okay? Okay. Now, we have seen together that in general, it's we have a simple solution when we have adiabatic end of fin. Okay, so that's why we'll do like a small, if you want, correction of the lengths in order to be able to use this condition. What do we mean by this? Okay, for example, let us consider the following fin, and this fin is not insulated at x equal L. But I want to have a simplified solution for my problem. I say the following: what if, okay, like I open, consider the following case. You have a rectangular fin of length L, okay, and you have convection from this side and also at the tip of the fin, at the end of your fin. But you want to do a model in order to use the equation of insulated tip. Okay, so what you can say, let me open, if I consider that I open the fin, instead of having the convection from this side and this side like this, I open it, I consider it had an extended length. So if you want, I just open this and I have an additional length here. Then I can consider that at the end of this additional length, I have insulation. Okay, and how to calculate this additional length that is doing convection? I consider the cross-sectional area, okay, of my fin divided by the perimeter. Okay, so this method is called correction of length. So for fins with convective heat transfer at the tip, a corrected length can be introduced in order to use all the equation for insulated tip. Because for insulated tips, the solution is relatively simple. Okay, so this model can help us to find, if you want, the heat transfer through the fin with a small error. Okay, by introducing the correction lengths. For example, let us take the case of a a rectangular cross section. If I give you so this is my cross section, okay, and I have this is the thickness T, and let's say this is the width W, okay, and I have convection at the tip of my fin, and I want to find what is the value of the corrected length. So all I have to do is the following. I say LC is the length, the actual length of the fin, and I should add to it first, what is the cross-sectional area here? It's W times T. So WT over the perimeter of my fin, which is 2T plus two W. Okay. Now, in general, okay, we have the case that the width is much larger than the thickness. So if W is much larger than T, okay, so I can say here I can neglect 2T compared to 2W, okay, and I end up with L plus WT over 2W, so I can simplify W, okay, and I say then that the corrected length is L plus T over 2, okay, and in this way I can now say I will use the developed solution for the case of a fin with the insulated tip, but I should pay attention to replace the actual length of the fin by a corrected length. Okay? Any question on this?
No.
No, doctor.
Okay. Okay. Now, once you have the equation of temperature with X, we solved for T varying with X by using the appropriate boundary conditions and solving for the differential equation. Once you have T function of X, how you can calculate the total heat lost by convection, especially in case of insulated tip. In case you have insulated tip, so the heat transfer here is 0. Okay, so the total heat transferred is only by convection through the whole area here. Okay. So what can we do then? We can say that since the temperature is varying, to find the total heat transferred by convection, we need to integrate. Why we need to integrate? Because if we consider this small element here, the temperature here is different than the temperature at this level here, okay? So for each small element, how can we write elementary convection, dq convection? So elementary convection through a small area is equal to H, which is the convective coefficient, times the perimeter. We need to consider now elementary area of exchange, dA, okay? But what is dA? dA is this area here, the whole area, okay? Through, of course, it will continue down and like this. So this whole area. This whole area is the thickness, this is small thickness, times the perimeter of my fin, okay? So I can replace dA by small thickness dx times perimeter of my fin, okay? Times, of course, Tx minus T infinity. So since T is variable with X, to get the total value of heat transferred by convection, Okay, I should integrate this. So if I integrate this over the length of the fan, so from 0, x varying from 0 to L, I can get the heat loss by convection. Now, of course, in case I don't have insulation here, I should say this is heat convected from this surface, and I should add to it the heat convected at the tip of the fan. But if it's insulated, then no heat is lost at the tip, and I just have to calculate this. Okay, so once I have the equation T function of x, Q is simply integral from 0 to L, HP times T minus T infinity dx. And we know that T minus T infinity is theta x, that we have already for different cases. We can solve for theta x using the boundary conditions. And as I told you, I will give you a table. So in the exam, you don't have, you need to know how to solve for C1, C2 from boundary conditions. But if they ask you for the temperature profile or for the heat transfer rate, you can use the table directly. Okay, so these are the main cases that we use in general. The first case is infinite fin. So L tends to infinity. When L tends to infinity, as we said, at the end we'll have adiabatic condition. So theta L is equal to 0. And this is the easiest temperature distribution. It's exponential E minus mx. Now, while if you do integration, and if you integrate to get the heat transfer rate, you will get m. What is m? M is given by the following formula. Okay, so this table will be provided to you. You just have to replace. So it's radical H. H is the convection coefficient. P is the perimeter of the fin. K is the conductivity of the fin. AC is the cross-sectional area of the fin times theta base. Theta base is, as we said, it's the temperature at the base of the fin. So at x equals 0, this is at x equals 0, minus T infinity. Okay, now in case you have the most complex scenario, as we discussed together, is that we have a limited length with convection condition. So as we said, the convective condition is written as follow: the heat flux at x equal L, so the conduction at x equal L, which is minus k d theta by dx, is equal to the convection at the tip, which is h times TL minus T infinity, or theta L. And in this case, you have the most complex solution, which is given here. So at any position x, this is the solution for your theta over theta 0. And of course, if you integrate, so by doing integral, you can get the total fin heat transfer rate through the corresponding area. Okay. Now, in case you have adiabatic condition. So as you can see, adiabatic condition is much simpler than this. That's why we use the concept of corrected lengths in order to use a relatively simple form. Okay. In this case, the solution is of the form m times tan hyperbolic ml. Okay. Now, for fins, we know we introduce fins in order to enhance the cooling in general or heating process. Okay, so we need to, and here we are considering cooling situations because we have temperature at the base larger than T infinity. So in order to enhance the cooling effect, we need to consider some parameters that will calculate for us the efficiency of the fin. Okay, so first, what do we mean by fin efficiency? And we will consider now the case of insulated tip, because the total heat transfer will be through the area of the fin, the lateral area of the fin, and we consider that at the tip no heat is lost. In case we have heat lost at the tip of the fin, we need to add it to the total heat lost by the fin. Okay, so the fin efficiency can be defined as the actual heat transfer over the heat that would be transferred if the entire fin area were at base temperature. What do we mean by this? This is the base of your fin, okay? What is actually taking place, why the fin can help you to evacuate heat? Because it should have high conduction. So if it's characterized by a very high conduction, it will allow you to propagate heat more within your fin. Okay, and as long as you have a high conduction, the temperature here will not drop a lot. Okay, so you will maintain a high temperature at the fin surface, which is good to evacuate more heat outside, because you know that convection is proportional to T at X minus T infinity. Okay, actually through your fin the temperature will drop. And as heat is convected and you have losses, okay, the temperature will drop within your fan. So as X will increase, the heat loss will decrease. Okay, but if you want to take the ideal case, so if we have a maximum, if you want transfer, the maximum transfer corresponds to the maximum delta T, which is T base minus T infinity. That's why we can define the fin efficiency as the actual heat transfer. And how we calculate this transfer? Can you tell me why we can consider that the total transfer is equal to minus Ka dt by dx at x equals 0? How we can prove this? Why is the total heat transfer, if we have an insulated tip, should be equal to the conduction flux at the base?
Doctor, may you repeat your question?
Okay. What is happening here in our problem? In our problem, we have the following. At the base, okay, we have a certain heat flux that should be evacuated. Okay, I will call it Q second at the base. And what is happening is, as if you want, the heat is going through the fin, you have at each dx you have some losses by convection. Okay, and here, as I said, consider an insulated tip, so no loss here. Okay, why we can consider that the total heat lost through the fin is equal to Q second at the base? If you want to do an energy, yes?
If the tip is insulated,
Yes, exactly. First, steady state. We have steady state case, okay? We have steady state case, so Qn equal Q out, okay? So you can say, since we have steady state, Qn equals to Q out, okay? Now, as we said, we consider an insulated tip. So here, no losses. Okay, losses Q out are through the lateral area of the fin. So we can consider that what is Q out here? It's the total heat convected through the fin, okay, between 0 and L. So this is the integration we did together before, okay? And what is entering the fin? What is entering the fin? The conduction from the base. So this is Qn is Q conducted at base. Okay. So that's why, if you want, in case you have an insulated tip, no need even to do the integral to find the total heat lost by the fin, because you can directly say that if I know what is Q conducted at the base, I can say that it's equal to the integral over the whole fin. Okay. If not, in case you have a non-insulated tip, then you can say that Q conduction at the base is equal to this integral plus Q convected at tip. And in this case, they should give you information on what is H, what is T at tip, etc. Okay, to be able to calculate this term. Okay. So this is about the actual heat transferred by the fin for in case of insulated tip. And as we said, what is the maximum possible transfer? The maximum possible transfer is if I have the total lateral area of my fin at T base, because this will lead to maximum temperature difference. Maximum temperature difference means maximum convection. So how I calculate this, I do H times the lateral area of the fin, and the lateral area of the fin is the perimeter of the fin times its length. So it's P times L, AL is P times L, times the difference in temperature. Okay, and we said the maximum temperature difference is T base minus T infinity, which is theta at x equals 0. So that's why you can say that heat that would be transferred if entire fin is at base temperature is HPL theta 0. And now if I replace in my equation dt by dx by its value at x equals 0, I get the following form that is given for you in the table. Okay, so this will be given for you in the table, but you should understand the physics. You should understand the physics, how to find this. I can ask you in the exam to do an energy balance, for example. Okay, so sometimes you can find your values in a much easier way. Sometimes you don't need to integrate, you just have to apply an energy balance and deduce what is the heat lost by your fin. Okay, so now if you replace Q in this equation, okay, you get the efficiency of your fin. So the efficiency of your fin is, because you'll have a lot of simplification, theta 0 will simplify, okay, and then you can say that the efficiency of the fin for this case is hyperbolic tan ml over ml. Okay, now we have several types of fin surfaces. The geometry of fin surface can vary. So it can be of rectangular profile, it can be of circular. So as you can see here, you have a straight fin of rectangular profile on a circular tube. Sometimes you can have a cylindrical tube with radial fin or rectangular profile, etc. Okay, so the geometry of the fin will depend on the case that we are considering. Now, for each geometry, okay, you have some, if you want, figures that can give you the efficiency. And for example, here, in case you have a rectangular fin, they can tell you graphically determines the fin efficiency function of the following parameter. So sometimes I can give you graphs, okay? In these graphs, all you need to get the fin efficiency, you need just to know the following parameter, okay? So the characteristic lengths. And as we said, because the case of efficiency is determined according to a tip insulation, then we can, to be able to use this graph even for the case where we don't have insulation at the tip, we use the corrected lengths. So as you can see here, for example, they are telling you if you have a rectangular fin, for the corrected lengths, use L plus T over 2. If you have a triangular fin, so this is a fin in form of triangle. In case you have a triangular form, yani at the end of your fin, you don't have an area. That's why in this case, for triangular case, you can consider that the corrected length is equal to L, to the actual length of the fin. Okay. And considering the parameter AM, they are giving you what is AM. AM for a rectangular fin is T times corrected length, while for a triangular fin, it's T over 2 times the corrected length. So it's just this area, if you want, okay? If I consider this area, it's equal for the rectangular case to T times L corrected, while here you have a triangular shape, so the area is T over 2 times L corrected. So once I give you the parameters of geometry, you can just calculate this term, and from this term, you can come to the graph and determine what is the efficiency of your fin. And this is a tool if you want to not do integral, okay? Because you can now say, if I know the efficiency from the graph, so I get the efficiency from the graph, okay? And I say, what is the efficiency? It's the actual transfer through the fin that is unknown, and I need to do integration to find it, let's say, over Q max, and we said that Q max is HPL times theta 0. So sometimes I can use graphs to simplify my calculations. So I just take this term to the other side, and once I get the fin efficiency graphically, I multiply it by HPL theta 0, so I can get the value of Q fin. Okay? Any question on this?
No.
Okay. And here, of course, if the geometry will change, okay, of course, the graph will change. And here you have, for example, a graph for the case of circumferential fins with rectangular profile. And here, as I told you, for each graph, they give you all parameters needed. And for example, I should give you the inner radius R1, the outer radius R2 for the fin, the thickness L of the thickness T of the fin, and the length L of the fin. Then you will be able to calculate the characteristics, the corrected lengths, and the value of R2 corrected. Okay, and then you can replace these values in your following term here. Okay, in order to get what is the fin efficiency, and after you replace these terms here, you can get a certain value of this parameter. Let's say it's 2, for example. And here, why we have several graphs? Because if R2 will change, and you can have different ratio R2 over R1. Okay, for each ratio, you have a different graph. So here, the ratio is for R2 corrected over R1. And R2 corrected is calculated as R1 plus L corrected, okay? So for each fin, you should first calculate R2 corrected over R1, and you should calculate this parameter. Then, for example, if this parameter is 2, and R2 corrected over R1 is also 2, you take this graph, you take the intersection point here, and you can read